lecture. So this will be 4 lectures, and starting out with probably just impurity scattering and transport in metals. So
Great. So probably need this.
yes.
Index this request on your laptop.
Oh,
Yeah, good. From window. You guys see it on there?
Max usually doesn't do this. They just go.
Oh.
But Leo was just. Well,
Yeah,
okay,
we said
let's
it's
see.
do you guys see the signal here? Maybe the 8. Oh, maybe we connected. Can we connect directly to the USB-C?
Sure.
Maybe. Select. It's seeing Crestron here.
Oh,
you guys see it now? There we go.
Yeah. All right. Hi. Thank you for for giving me a chance to speak here. Thank you for the introduction. As Leo said, please don't hesitate to ask our questions anytime. Middle of the sentence, doesn't matter, right? The more you ask, the better I feel. So the organizers asked me to talk about basic stuff, meaning that SYK, non-Fermi liquids, will be covered by someone else, which is just perfectly fine. I thought I would start with Fermi liquids, but then I thought, well, maybe it's too much. Let's start with Fermi gas. So for the first probably 1.5 lecture, I will be talking about Fermi gas coupled to impurities and phonons and also magnetic moments. So it's not quite Fermi gas, but at least it wouldn't be about electron-electron interactions. And I really start from the basics. I really start from 1950s. Okay, but that would be too boring, right? So as in Stanislavski theory of theater, the actor has 2 goals. One is a goal, and the other one is a super goal. In a goal, I'm coming to a table, I'm opening my bottle of water, I'm taking my sip. That's a goal. What's a super goal? It's to show my emotions while I'm doing this. Okay, what's on my mind? What I'm really doing when I'm opening my bottle of water. And I'm going to kind of pave the way to something which is more modern and still active. And although I'm not going to show off my recent work, but somehow this basic stuff about phonons and disorder do go to something which I am interested in up right now. And the super goal that we're going to reach will be the subject of resistive anomaly near our classical second order phase transition. And this is the recent work that I did with my friends Vladimir Yutson and Christian Batista. And as you see, this is fairly recent, just has been accepted in RPRL. But in order to get there, we'll have to really go through basics of electron impurity scattering primarily, and a bit of phonons. Okay, so that's my goal for the 1.5 probably of lectures out of 4. As Dibanjan said, the lectures are posted. They're full of typos, plenty of them, and there is much more stuff in there that I would be ever physically able to present. But please give me some feedback. It would be very useful. Okay, so what is this resistive anomaly? Just a flash of slides. The subject starts in 1932, where Walter Gerlach, that same Gerlach from Gerlach and Stern, observed that the resistivity of nickel has a very well-defined feature when you go through TC between the ferromagnetic and non-ferromagnetic phases. So what's shown here is actually d rho dt to make it more pronounced, and you see a sharp R cusp. And since then, the subject has been studied to death. There are more examples. You have same nickel, you have cobalt. It doesn't have to be a ferromagnet. It can be also an anti-ferromagnet. Our more recent example, this is iron pnictide. And it also doesn't have to be magnetic. This is an example of a structural order disorder, a transition in a beta brass, copper zinc. And remarkably, in order to understand what's going on here, one has to abandon the cherished notions of the standard Boltzmann equation and do something else. Okay, so we'll start with cherished notions. I will give you some counterexamples how we think it's supposed to work, but it doesn't. And then we'll try to explain at least some of the observations here. All right.
The T over theta naught, is that theta naught or theta divided second?
This is TC.
The theta naught.
Curie. Yes. So here it's TC. Okay, that's actually, I'm done with my PowerPoint. And yes, classical phase transition, second order, all of these are second order, nothing about our quantum. Right? So all the surprises will come at a classical level. All right, so now, since I mentioned words disorder, let's start with canonical law, how we think about scattering by disorder in the framework of Boltzmann equation. We'll also do some diagrams, but let's start with something really simple. Okay, so probably everyone knows something about the Boltzmann equation, that as any equation has the left-hand side and the right-hand side. The left-hand side is the evolution of the distribution function in time and in space. If we apply electric field, let's say we have the force term, and then there is a collision input. Okay, we're going to be looking mostly at the static case. So df dt is equal to 0. To begin with, we'll start with the uniform case, especially uniform. So del f k is also equal to 0. And the electric field is weak, so that we can expand. We can replace f here by the equilibrium function. And then when you differentiate this, you get a factor of velocity. And then your Boltzmann equation becomes very simple. By the way, f is a distribution function for electrons with momentum k at point r and time t, right? Okay, so the problem is how to write down this guy, which describes our collisions. And let me run you through the usual lore, how this is introduced in textbooks. And I'm going to tease you now. I'm going to give you the lore, and I'm going to tell you that it's wrong. But not before you will tell me how it is wrong, okay? All right, so what's the usual lore? We say that we have electrons, they scatter, it's some junk. We describe scattering probability, assuming that it is known by some function of the initial and final momenta. And then we compose this guy as basically your ledger. There are processes which lead to increase of number of particles with given momentum, and there are processes which decrease the number of particles with given momentum. So we need to count the inflow and outflow. It's basically an accounting problem. All right, so how it's solved in textbooks? Not solved, but presented, is let's say we are watching a fate of a particle with momentum k. This particle will scatter into some other state with momentum k prime. So we need to throw in a probability from k to k prime. And this is going to go with a minus sign because we lose particles in a given state. And of course, we have to sum, integrate over states where the particle is going into. But we learn of quantum statistics also, right? Okay. So F basically gives you a probability that a given k state is occupied, but I need to go to state k prime, right? I need to make sure that the state is empty for fermions, or that we account for other particles in the state for bosons. So let me then multiply it by a factor 1 plus minus fk prime. Minus is plus is for bosons. Okay. What's with the plus sign? The plus sign, we have reversed our processes when particles from state k prime scatter into state with momentum k, and there is a probability of going from k prime to k. Everyone is happy with this one? Okay, yeah, I'll be more happy with Metro. Good one. So we have single particle, right? Because there are no other particles, and the single particle is moving in a potential profile. Little I. Oh, this one? EI, electron impurity. Thank you. So we have a single particle which is moving, something like this, scattering one particle only.
Where's F0 here?
This one? 0 means equilibrium. Thank you. Yes, still a function of k. Yes. That's how it is put in the notes. Still a function of k, but only a function of energy, not of other direction.
What are the properties of W?
We're getting there. We're getting there. But first I want to, yes.
1 minus plus F2.
Yes, good. You started to smell a problem. Why there should be there any information about other particles? Because single particle doesn't know whether it's fermion or boson unless it meets other particles. But the conventional law tells us that we should do this. What's the next step? Next step says, oh, it's obvious that from k to k prime should be equal to W from k prime to k. It's obvious, right? It's called, by a long word, micro-reversibility principle. Micro-reversibility principle. Okay, so if we do that, call it micro-reversibility principle. Then the nonlinear terms cancel out. You have one fk times fk prime, and another one fk prime times fk, and the overall sign here is opposite. Oh, and everything is simple. Our collision integral is reduced to a rather simple form. Now it doesn't matter which one I start with, K prime, okay. Quantum statistics disappeared, as you wanted. Okay. Question is, who told us that we have this micro-reversibility principle? If you solve the firstborn approximation, you will find that it's always there, regardless of any other symmetries in other problem. But let's not stop at the firstborn approximation and ask what are the actual symmetries of the system which go into this. And there are two symmetries which go into this. If the system has time reversal symmetry, then on time reversal, I should flip the directions of the momenta and also interchange them. If I have inversion, I should just flip the directions of the momenta without interchanging. So flipped W minus K prime. Now, if you combine the two, yes. Yeah, sorry, thank you. So if we now combine the two, the time reversal and inversion, then you do end up with micro-reversibility. Good. But it's not given that we have either of those. We can have a magnetic field, or we can have a system without the inversion center. So in general, W of K prime K is not equal to W K K prime. And therefore, micro-reversibility principle is actually not a principle. It's a consequence of two symmetries. If I don't have this micro-reversibility principle, then the issue of a particle knowing about its statistics becomes relevant, because the two bilinear terms don't cancel each other. And let's follow the consequences of this. Let's look at the case of bosons, where the occupation number of any state can be infinitely large. I can put as many bosons as I want into any given state. Then the collision integral will be strongly nonlinear, because if I'm in a state where all occupation numbers are much larger than 1, then I have product of fk prime wk prime k plus fk prime k prime fk prime fk wk prime k. Taking also the, let's say we restore the time derivative, and we put one particle into the system and we let it go, right? Because we have now a nonlinear equation of evolution, any nonlinear equation will run into an instability. At some later time, there will be some bifurcation between different states, et cetera, et cetera. But we're talking about single particle moving in potential. If we solve the same problem by using the Schrödinger equation and then take the semi-classical limit of this, the result will be totally unambiguous. So what's wrong with this equation? It's just wrong. This is not the right collision integral. It was made up by a physically plausible argument, but it has never been derived. If you start to derive the right collision integral, remarkably, you end up with this simple expression here, which works for any statistics, because it shouldn't matter, and for any kind of symmetry in other system. Okay, so this is the right starting point always, which was shown by Kohn and Lattinger two papers. 1957, 1958. Okay, it wouldn't really matter for us, but just to set the record straight, right? Where do we start with? So we start from here. Yes?
I'm not understanding the argument why this should matter. Why? Yes.
Because statistics is only defined if you have more particles than one in the system. This is just single particle problem. Other particles, they don't know about each other.
Why is this single particle?
Well, I have potential profile, and let's say an electron scatters from this profile, and we don't look at electron-electron interactions. So you might as well say that the electrons are not there.
Okay. But even if you're not looking at electron-electron interactions, the behavior of the transport of many electrons through the system would depend on the fact that
Fermions or bosons. No, the thermodynamic properties will, but the non-equilibrium properties not, because you really follow the fate of one particle. And then once you know the single particle distribution function, you multiply it by the velocity, you calculate the current, the whole current, etc., etc. So everything follows from this single particle. F naught, yes. F naught is different, yes. F naught may be Bose, maybe fermion, maybe anion, whatever. Yes.
But any corrections
Any corrections will be independent. Yeah.
Is there an easy way to see that?
As we'll see, the solution of these equations will be independent of what we start with. Yes.
So suppose you scatter from a K mode to a K prime mode, right? And you have fermions. If there is a fermion in K prime mode, the Pauli exclusion principle would tell you that.
No, because this is elastic scattering. It means that the energy of momentum K is the same as the energy of momentum K prime. And then you are guaranteed to have a freedom to scatter into the state.
So there would be no occupancy of K prime.
Yes, yes, yeah. So K, so first electron took space K.
Yeah.
Okay, and then it has energy epsilon K. That means that this energy always belongs to the same fermion.
Underlying quantum theory, shouldn't we have?
Sorry, underlying
Quantum theory.
Okay.
Shouldn't we have micro-reversibility due to chromaticity?
Well, if chromaticity follows from time reversal and an inversion, right, then it will be the same thing. But chromaticity by itself would not guarantee micro-reversibility. For example, you can have a triangular impurity of this kind, right? And let's say I go with momentum K from this side, and I scatter into K prime, right? But now if I go from this side, and K prime goes in here, K is like this. So obviously there is no micro-reversibility, although the system is Hermitian.
So if I have a state at K which has an energy epsilon K, I would also have a state at minus K energy epsilon.
Minus K, which is, yeah.
Say. So then that scattering would be completed, right? K going to minus K would be completed because there's already a state there.
No, so we move on an equal energy profile. So let's say this is epsilon K equal to a constant. And this is the initial state, and this is final state. And because you don't change energy, you don't stomp on other people's feet. You are within your bounds. You are entitled to be in this state as well as in this state, because energy is the same. Yes. No, that's fine. That's fine. That's fine. No, this integral without micro, I think it's shown in the notes that it conserves the number of particles and energy, because this is like, yeah, so, yes. If it's boson, okay. It's just to make the argument more obvious, but the non-linearity will be there even for fermions. All right, so we are now in 1958. Okay, let's move up a little bit. And now this is our collision integral. And let's apply it to the simplest case of isotropic scattering, which you have for the case, for example, of point-like impurities. For the case of isotropic scattering, the scattering probability does not depend on anything, it's just a constant. So we take it out, right? And let me also define the scattering probability with the energy conservation law, because we're talking about elastic scattering. So we should have this delta function inside of our collision integral. Okay, so the integral over k prime splits into two parts. There is an angular part, and there is the part over the magnitude over the momentum, which is energy. We average the distribution function at state k prime over angles, right? And we don't do anything with the function at k because it's not part of anti-collision integral. And then the integral over energy with delta function gives us density of states. So this becomes W density of states at energy epsilon k times the difference, average F minus actual F. And average F only now depends on the energy. And let's call this our combination 1 over the scattering time. This is the scattering rate. Okay. This form is very familiar to another popular form, which is used in many textbooks and papers, which is called relaxation time approximation, RTA, which is almost the same as this one, except for, well, I'll put some other time here, except for the average function, which is not an equilibrium function. We have an equilibrium function, is momentum k minus fk. Raise your hand if you saw this form somewhere. Great. What are the problems with this form? Well, what's going on here is pretty much obvious. Let's say if we apply electric field, give extra momentum to the system. The distribution function becomes anisotropic in momentum space. And then we have scattering by disorder, which is elastic. What it does, it randomizes at the directions of electron momenta. It cannot change the energy. So the best it can do, it can convert an anisotropic in inequilibrium function into an isotropic one. But this is still not a Fermi function for the case of fermions. This is just angular averaging. Whereas here, some R process takes care of everything. You start with something non-equilibrium, anisotropic, and you end up with equilibrium and isotropic. This process, therefore, must involve inelastic scattering, because without changing energy, you wouldn't be able to reach equilibrium. Okay. Well, the number of particles is always R conserved. Okay, how do R conservation laws show up in this akinetic R formulation? Suppose that I have a quantity Q of K, and let's say it can be 1. In this case, it's going to be number of particles. I have, or it can be K, momentum, or it can be epsilon k, which is energy. Right? Okay, so if I take the full Boltzmann equation and multiply it by this R quantity, then on the left-hand side, I will have total derivative of the distribution function multiplied by Q of k, which is time derivative of either total number of particles or total momentum or total energy. And on the right-hand side, we have the integral of the collision integral. If little q is conserved, the integral of the collision integral with q must be equal to 0. So this is the R conservation law. Okay, so what do we conserve in the process of elastic scattering? We conserve obviously the number of particles. We conserve total energy. And we also conserve the number of particles with given direction of momentum. Sorry, with given energy, right? Because energy doesn't change. Okay. Therefore, the electron impurity or collision integral should vanish on averaging it over the direction of k. Okay. So when I just average over, let me specify that I'm only doing it over the directions. So this is only the angular part of the integral. Then the corresponding R quantity is the number of particles with given energy. And that should be R conserved. Let's check the first R collision integral. If you average this difference over the angles, you get 0. Right? Because this is already average. Average minus average is 0. If you average this over angles, nothing is going to happen. Right? Okay, so the number of particles with given energy is not R conserved. That's kind of an issue because diffusion, which we expect to set in at some later stages, is a process in which the energy of particles which going through some up profile is R conserved, but the momentum isn't. Right? But we need to conserve the number of particles with given energy. That means that in the long time limit, the Boltzmann equation with the collision integral of this type will give us the diffusion mode, while this one won't. Now, this is really an issue because it does give incorrect up results. Also, we do not conserve the total energy here. If I multiply the right-hand side by the energy, integrate over the momenta, the left-hand side is not equal to the right-hand side. Here, we conserve the energy. Okay, sounds pretty scary, right? That's what we learned in textbook, Nashcraft and Merman, and applied many, many times, comes with serious faults. Yes?
So, so this has not some implied temperature, something, right?
Yeah, it's an equilibrium function.
So, is the idea that if you want to conserve energy, adjust the temperature so that it does?
No, conservation of energy simply means that you take the energy multiplied by the collision integral, and you get 0 because the total derivative of total energy is equal to 0. No. No, so at given temperature, so here the system is an, if relaxation time approximation, you are saying somehow that there are processes which are both elastic and inelastic, and somehow all together they take you to equilibrium at given temperature, which, okay. So here there is not even a notion of equilibrium, because without inelastic processes, you cannot establish it. All right, so where that can play a role? K, yeah. So think of the collision integral as a function of K. So you multiply it by something which is also a function of K, and then sum over k. K prime is the internal variable. Right. So we know that the left-hand side must be equal to 0. Therefore, the right-hand side must be equal to 0. And so when we construct our collision integrals, we need to make sure that we satisfy our conservation laws. All right. So, yep.
I guess diffusion works differently for the two different quantities.
I'm sorry?
Why does diffusion work differently for the two different quantities?
There will be no diffusion in RTA, period. If you you can pose the following problem. You can inject one particle into system at time equal to 0, r equal to 0, given momentum, and then you follow the fate of this particle. If you solve RTA under these R conditions, you will find that everything relaxes exponentially to equilibrium state.
That's if you don't have the F naught. If you have F naught, like that particle will stay there forever. So I think you lose energy.
You lose energy, yes, but you wouldn't. Okay, so by diffusion, I mean something specific. If I look at F, which now I allow to depend on position and time, and I do Fourier transform Q and omega. So now this is F K Q omega. By diffusion, I mean that if I take the limit of very small frequency, namely omega tau much smaller than 1, Q times velocity, let's say Fermi velocity times tau much smaller than 1, I should develop a diffusion pole, where D is the diffusion R coefficient. D is a spatial dimensionality. There is an appendix in the notes which shows that if you start with this equation and you find the perturbation due to delta function, which is basically a Green's function of this equation, then in this limit you do recover at the diffusion pole. If you start with this form, you lose half of your R solution. You will have only exponentially quick up relaxation without long time diffusion, right? So what's important is that when we're looking at our problems in which the external forces are inhomogeneous, that become crucial. For example, if we look at ultrasound absorption, we have a sound wave which goes through a metal and electrons absorb sound. The wave number of phonons is substantial because their speed is so small. So what you're actually measuring in this case is the real part of the charge conductivity at finite Q and omega. This is absorption of ultrasound. Okay. If you do it in the RTA, you get a wrong result. In the problem which I posed as my super goal, eventually I will also have to deal with an inhomogeneous electric field. And in this case, if I do RTA, I'll fail. Okay? But there are, fortunately, situations where the difference between the two doesn't matter. Okay? And this is a situation when we apply a weak, uniform, static electric field. Actually, it can be dynamic. But if electric field is uniform and weak, RTA and correct our collision integral give you the same conductivity. Proviso that when you do this kind of theory, you pretend to know what the scattering probability is because you have some little theory for little impurity and you can calculate the scattering probability within some kind of Born approximation, right? And here it is entirely phenological. So why it works? Okay, so let's write down the Boltzmann equation into forms. This is correct. This is RTA.
There will also be the wave of the F naught on the side.
Oh yeah, sorry. Absolutely. Okay. And all we need to know in this our problem is what the conductivity is, which is what is the current. And so I will multiply now the right-hand side and left-hand side of these equations by minus twice E V, 2 for spin, so I want to calculate the current. And on that, the isotropic part of the collision integral simply drops out. Whereas the integral of F just gives me the electric arc current. Let's make them the same, but okay, can be different, but they are in this case phonological parameters. So when we are only looking at small deviations due to uniform field from equilibrium, it doesn't matter which function of energy we start with, right? I can say that my F, which is non-equilibrium, is equal to some function of energy only plus delta F, which is anisotropic and it's proportional to the electric field. What I put here in this case doesn't matter. It drops out anyway, and we have the electric arc current given to us by the usual E squared. Okay, so the conductivity in both cases is going to be, let me write more general formula than you probably usually see. So in this case, I did not assume that the spectrum is parabolic. This is the density of states, d is the spatial dimensionality. Okay. So most of the time, if I just dealing with this kind of problems, RTA is fine. But keep in mind that it can be dangerous. Yes.
Why did the electric field need to be uniform and weak?
Okay, weak because I need to expand. Right? Uniform because as long as I have finite Q, I need to watch for the diffusion pole, which I know is not there in the RTA case.
But for diffusion, the conductivity doesn't seem to matter anyway.
Yeah, so for DC, linear, uniform conductivity, right? If you talk about something like sound absorption, you need to know the conductivity at finite wave number. Okay, then. Yes. Sorry, non. Yes. Yes. Well, okay, that's actually a very good point. What do we mean by the field? What do we mean by the electric field? Because there are two kinds of fields. One is the external, which we apply, right? And the other one is the field of all impurities which are there in the sample, right? They don't have to be charged. They can be screened, but still they produce electric fields of some higher multiple moment, right? And so generally, the electric field in a sample is always non-uniform. We make it uniform by averaging, and that's going to be an issue. Number 3, the Boltzmann equation, even in the correct form, because of this, and correct form because we did not use micro-reversibility, it will fail to describe a very simple situation where instead of one type of a disorder, I have two. And one of them is short range, and the other one is long range. Okay? Which is the case for the resistive anomaly. You have normal scattering by phonons and impurities, and you have long-range fluctuations of the order parameter. Naively speaking, you should just add up the scattering rates, but then you wouldn't get the right anomaly. Okay? And the issue is, when do you average? When we say that we have this Boltzmann equation, what do we mean by F? Well, if we started with a Liouville equation, it would be an exact equation of motion of a particle in a given potential profile, right? It's going to be as random as the potential profile itself. Right? Well, here we replace it by some nice R quantity, which we implicitly averaged over realizations of disorder, and we lumped all disorder into the scattering probability. That doesn't come without cost. Okay, so we'll talk a bit later. All right, so this is how it looks at the level of the Boltzmann equation, and of course one can do more things. One can consider a scattering which is anisotropic, that is, scattering probability is a function of the momentum transfer of the scattering angle. As an exercise, you will be able to show that in this case, you simply replace tau in the conductivity by what is known transport time. And transport time, its inverse, is related to the scattering probability multiplied by a weight, which is 1 minus cosine theta k prime. This is the scattering angle between the two. Okay, so when this is important, it's important when a scattering is of forward type. So this is the opposite case to isotropic scattering here. For isotropic scattering, well, all outcomes are equally probable. Here, the scattering probability is strongly peaked at small scattering angles. And therefore, the typical value of this angle is small. So I can expand to second order. And because the angle is small, that weakens, or this makes the integral smaller. So if we introduce 2 times, one is going to be what used to be tau for point-like, but if it's not even point-like, I can still introduce this time without the 1 minus cosine theta factor. This is known as quantum time, or single particle time. It's called R quantum because it has no manifestations at the classical level. It shows up as the width of the spectral function. The width is given by 1 over tau single particle. It shows up also in quantum effects such as magnetic oscillations. It controls the magnitude, the amplitude of our quantum magnetic oscillations, Shubnikov, the Haas, and the Haas-1 alpha. Okay, but in general, if the 2 times are not the same, and they're not the same as long as scattering is not isotropic, then it is the transport time which enters all transport R quantities: diffusion R coefficient, conductivities, viscosities, etc., etc. There's a good reason for that. The Boltzmann equation doesn't know yet whether we're dealing with a quantum case or a classical case, right? So it should be applicable to a completely classical system of classical gas scattering from some hard spheres, right? Okay, if you remember your classical class mech, the quantity which we calculate here must be proportional to the total scattering cross-section, because we think about this as a differential across section, sum over all scattering angles, and you get total across section, right? For hard sphere, cross-section is finite. For hard disk, cross-section is finite. As long as potential is not artificially cut off at large distances, but extends all the way as any function of R, total cross-section in classical mechanics is infinite. Why? Because I have a scattering center, I have a particle which is coming in with some impact R parameter B, and then what I do, I change B by B plus dB, and the differential cross-section is equal to 2 pi B dB. Total is going to be an integral over all impact R parameters, and because my potential goes all the way to infinity, I have to integrate from 0 to infinity here, and the result is infinite. This is an inadequacy of classical mechanics, because at very large impact R parameters, the scattering angles are small, they become comparable to the diffraction limit, and at large distances, at large impact R parameters, our quantum mechanics should kick in. But as long as we don't involve our quantum mechanics, we have an infinite R cross-section here, and at the corresponding time would be also 0, or 1 over tau would be infinitely large. Okay, so then this has nothing to do with semi-classical physics. It can show up only in a quantum phenomena. Oh, so transport is only the one, right? So this is the rigorous definition of transport time. If scattering is isotropic, that means that this guy is a constant. Cosine theta drops out on averaging, and then the two times are the same. If scattering is of forward type, then 1 over tau transport is going to be much smaller than 1 over tau single particle, because in order to affect transport, effectively, you need to come back, right? So there should be some back scattering. But for forward type scattering, it will take a very long time to make a U-turn, right? Whereas single particle time counts all scattering events, large angle and small angle.
Is single particle time relevant for anything?
Beam propagation. Let's say if you have a beam of classical particles going through, then the angular spread of the beam are controlled by at the cross section. But then it turns out that there is a funny game that the impact parameter cannot be larger than the width of the beam. Okay, but if you simply solve the Boltzmann equation for hard spheres, which scatter from any potential with finite support, that is going all the way to infinity, then no, it doesn't have a place in kinetics. Right. So that's why our quantum. So as long as the phenomenon is a quantum, actually it's not relevant for weak up localization, because this is still a transport phenomenon. But it's relevant for magnetic oscillations and the line widths of ARPs. No. So then there is our condition. If the potential falls off faster than 1 over r squared, total cross section is finite. Right. Classical is always infinite. Yeah, always, because you have to take into account all impact parameters from 0 to infinity. Yes, yes, it is just the same thing, up to factor of 2 and the minus sign. Because it shows up in quantum phenomena only. Self-energy, well, self-energy, of course, that, but the fact that the spectral function has a finite width, it's a quantum phenomenon, right? Because particles are not precisely on the mass shell. Classical physics doesn't know about spectral function, right? So in this sense. Whatever you want. So if you take 1 over tau is going to be infinite. Because you have collisions at any impact parameter, and they pile up, and the scattering rate become infinite. We always measure differential across section, right? For example, in medium range nuclear physics, which is essentially semi-classical, we measure the differential across sections.
How much is
Entirely. Has nothing. Well, see, okay. Let's go back here. I formulated this problem as a way to find the R conductivity, which I did, right? I gave you the answer for the R conductivity. Did I give you the answer for the distribution function? No, right? It is valid, it is known up to an arbitrary function of energy, which I cannot determine if I don't take into account inelastic R collisions. For linear uniform electric field, I don't care. But if I had to solve the problem with, let's say, a non-uniform field, that would be a self-consistent R condition.
Tau depends on F bar, right?
Sorry?
Tau. Your sigma depends on tau k, right? The tau k depends on F bar.
Sorry, its K was from tau is a function of energy. When I substitute my solution into the current, right? Everything is proportional to F naught here because I will have to take an integral. So the notion of the thermostatistics will come from the integrand, but I don't know what my F bar is. Right? It's much more complicated problem. I really have to invoke inelastic processes. Tau depends on, let's say, Fermi energy. So everything here, so I quickly take a limit when the temperature is much smaller than the Fermi energy, then everything in this integral is projected onto the Fermi energy. But in principle, it's function of energy. So tau is a function of energy.
Is if you try to use the formula for tau single particle, but for a classical problem, then you get an incorrect answer.
Well, it's not that. If you really solve the classical kinetic problem, you will see that total across section never shows up in the answer. And this is because of the structure of the collision integral. If I had only one term, let's say, the loss term, right? Suppose that I have a system in which I'm only losing particles in state K, right? Then I have an integral over K prime. K prime acts on scattering probability, and that seems to be the total across section, right? But I have also the gain term, and the two balance each other, right? So accidentally, for isotropic scattering, I will get a result which will look like total across section. right? But in fact, it was transport across section taken in the limit of isotropic scattering. So isotropic scattering also means that, let's say, if I have a hard sphere, right, scattering is isotropic. In this case, total across section is finite because the radius of the sphere is finite, right?
So if I had a system where there was electron impurity scattering, but also some much slower inelastic process, then eventually I do want to relax to F0.
Yes.
The tau star that I put into the relaxation time approximation, should that still be the tau, or should that be some much longer time?
I don't know. It's an ad hoc. So one can also in the appendix, I think there is a way how to reconcile these two approaches. And if you do this, the answer will be that it's the sum of the inverse taus. So as you said, let's solve a problem where we have elastic scattering and also inelastic one, which will model in RTA. Okay, let's solve it. So we'll have f of k will be equal to f bar tau elastic plus f naught k of tau inelastic. Sorry, getting ahead of myself, right? Plus b e f naught prime divided by 1 over tau e. Elastic, sorry, this is not e, this is elastic plus 1 over tau inelastic. Solved, right? Okay, so now in order to get f bar, I need to average. When I average, the fourth term drops out. Then you can check in 1 second that f bar is equal to f naught. Okay? And then the inverse sum, so the sum of the rates gives you the total R conductivity. After that, I can take tau inelastic to infinity and claim victory.
Is tau something that can be measured independently from the conductivity? Louder, I think.
It can time be measured independently of a conductivity. Okay, single particle time can be measured from the amplitude of Shubnikov that has oscillations, let's say, in a transport environment. This is actually a very useful measurement because from mobility you get the transport time, from Shubnikov you get the quantum time. Look at the two, and how they differ tells you how long range your potential is. Okay? One can measure diffusion coefficient it's still transport, but it's not linear transport. It's called focusing. You have a sample with 2 R contacts, you inject the current into 1 R contact, and you do it in the presence of the magnetic field. And so here is going to be your collector, and the only trajectory which will contribute to the current in the collector is the one which just fits in there. So from there you can work out what the diffusion coefficient is. Okay. There is also a way to measure the diffusion R coefficient in disordered superconductors, because there the mean free time enters the effective correlation length. So from the slope of HC2, one can also infer the diffusion coefficient. But by and large, is of course transport. That's why it's called so. Yes. Sorry.
You just showed there that if bar and if not are equal.
Well.
What are the atoms?
It's a model case, which is a kind of a pacifier. I know something about this part, then I bring in inelastic processes in the simple model form. If I do so, I end up with this, our conclusion, right? If I would really treat inelastic processes as they should be treated, while the integral equation, of course, it wouldn't be such simple thing, right? So this is kind of, it's a gross simplification of the problem.
Why the inelastic scattering always glowing?
Not only, because you can imagine an inelastic process which doesn't relax the direction of the momentum. But in order to reach full equilibrium, you need to relax both the directions of the momenta and the magnitudes.
But is it possible that this inelastic scattering might have broken or not?
Well, it depends on the thermostat, right? If your thermostat are phonons, right, then the inelastic term will relax you to an equilibrium distribution with temperature equal to the temperature of phonons. You can have two thermostats. You can have one thermostat for electrons and the other one for phonons. They don't have to be equal, right? In this case, you can have a two-temperature system. Okay, that's subject of the last two lectures, right? None of this is worked. Yeah, Josh. Sorry? No, for any. So if you replace tau by a tau transport, this is your diffusion coefficient.
That can be derived, that's the vertex for short range.
Well, I didn't say anything about vertex. No, so this is how the distribution function should look like at long times and at long distances, right? And the statement is broader than point-like impurities or short range. Yeah, doesn't matter what the diffusion coefficient is, it should flow into this form. Since
So it always has to match the time.
yeah, always has to match time in the arc conductivity, right? Well, since Josh mentioned vortex arc corrections, let's look at the same issue, but from the point of view of Feynman diagrams. We'll need this. Okay, any questions on the Boltzmann part? Yes. In this model, yes. Well, I'm still using RTA. This part is solid. This part is ad hoc. If I combine solid and ad hoc, so I didn't fix any of the RTA problems. It does not conserve the number of particles with given energy, et cetera, et cetera. But now I say that, well, it shouldn't, because it mimics some kind of inelastic process. But mimics is the word, is the key word, because the actual Boltzmann equation for any inelastic process, be it electron-electron, electron-phonon, is an integral equation. Because energy changes, there is an integral over energies. It never reduces to an algebraic form. So this is a poor man model. We're all poor men here, okay? We like to use it.
How inelastic goes to infinity, then the inelastic collision is zero.
So I can keep them on equal footing, or if I don't want, so let's say I want to solve this problem only. Well, if the solution means that I gave you the full distribution function, meaning that f bar is to be found, then I need to introduce this term, find f bar, find in this model that it's the same as f naught, and say that, okay, now I solved the problem, right? If I only wanted to do arc conductivity, I didn't need to do this. if the electric field, well, depends on what you find, what you call good. Maybe I can give you an example. Just one slide. Okay, so this is a comparison of a particular transport R coefficient, which is called Nernst R coefficient. Nernst is something like this. You apply a temperature R gradient in the y direction, in the presence of magnetic field, which is along the z-axis. And you measure the electric field along the x-axis. So it's kind of a thermal power. It's the whole effect for thermal power. And then the Nernst R coefficient is the ratio of Ex over temperature gradient over V. Okay. And so you can calculate this within the Boltzmann equation. So what you assume here is that you have elastic scattering at impurities with some finite range arc psi, right? And in this particular study, which is by Karl Binneker and his then student Pikulin, don't remember his first name, they took a square lattice with first, second, and third neighbors, right? And they compared the exact numerical solution of the Boltzmann equation with the prediction of RTA. Red is the exact solution. Okay. Red is the exact. Dotted is tau k. Tau k stands for RTA. Judge for yourself. Not very good. Zeeman is a fix, kind of in between. Yes.
So when you say RTA, you're really talking about relaxation, this global.
Yeah, so RTA is just that.
Because one might also call the FR model of relaxation type.
I will never do that. I will never do that. No. Because this is bona fide our collision integral as given to us by Kohn-Lattinger, right? And this is its simplest form, but we could use it for any kind of scattering, any kind of lattice, etc., etc.
But I guess you could still say, like, you guessed the form of W.
There are good news and there are bad news. Of course, if you want to calculate something and it doesn't really matter for you whether the effect is 20 or 25, then it's fine. All calculations, I think the matter of a principle is more important. So here we're talking about numbers. Numbers are going to be different. But in things like ultrasound absorption, you will get just totally incorrect results. Right? You cannot match them. Everything, so this is its phonological definition. You can calculate it. And because so the Nernst setup only differs in how you prepare the left-hand side of the Boltzmann equation. You need to introduce magnetic field, you need to introduce the thermal gradient. The right-hand side is the same. And so taus will show up. So there is one last thing about this is what if we have a lattice, which we always do, right? And let's say we have lattice. So a dispersion is anything you want. It's a band a dispersion. And also the scattering probability is an arbitrary function of k prime and k. Well, the Kohn-Lattinger collision integral still applies. I will pull out factor of delta function due to energy. Okay, and let's say on the left-hand side, I still have the driving force here, right? Now, if the scattering probability is not isotropic, so if it's isotropic, we solve the problem just in one go. We multiply the left-hand side and the right-hand side of the Boltzmann equation by the velocity. The right-hand side immediately gives us the current. If the scattering probability is not a constant, I cannot do that, but then if the system is isotropic, I can rely on symmetry. And symmetry will tell me that F can be only written as, let's say, some function of energy, which we don't care, plus, because it must be, because a deviation from the equilibrium is due to electric field, it must be proportional to the electric field. But electric field is a vector. So we need another vector to dot it in. And in an isotropic system, there is only one vector, which is k, or at the velocity with momentum k, which are the same because they're parallel to each other. So I will just choose this as vk into E times something else. And this something else is now a function of energy only. And plug this in, solve for G, and you will get that G is basically the transport time, right? If the system was on lattice, I cannot do this anymore because there are infinitely many vectors in the system. And by symmetry, I cannot constrain my solution to have a simple form. And unfortunately, in this case, there is no way around of solving the Boltzmann equation numerically. The RTA in this case will tell you that you have to use this form, where tau is a function of k point in space, somewhere in the Brillouin zone, comes with the same problems, does not conserve the number of particles, etc., etc. Right? Okay. So what was done here, numerically, it was the numerical solution of this equation, which is not reducible to anything simpler, unfortunately. All right. Let's have another look. How do we go about this by using the Kubo formula? So I presume that you have some background knowledge of the Kubo formula, but let me throw something at you to see if it goes. So let's say I have some impurities in my system, scattered randomly, but I'm looking at one given realization. And at one given realization, I have some potential U of R. And I can solve my Schrodinger equation. I need a Green's function. So I'm just solving H, G equal to minus I. And let's say I know this Green's function. Let's say at some frequency omega, which is a function of 2 points. Because if I start at some point R and I end in point R prime, it matters not only how long did I travel, but also where I start and where I ended, because my system is not spatially uniform. Of course, we never know this Green's function in reality unless we do a numerical calculation, because it is just a Green's function of the Schrodinger equation and very complicated disorder profile. But once I know this Green's function, I can calculate the average conductivity. In the Kubo formula, the conductivity is our convolution of two Green's functions. I haven't averaged over disorder yet. So I have a product of GRR prime, GRR prime. Then diagrammatically, it's a bubble. This point I have a current vortex, which is, let's say, delta R component alpha. In this point, I also have delta R prime component beta. Okay, so this is point R, this is point R prime, and this Agrins function is this line from here to here, and this Agrins function is the Agrins function from here to here. Okay, now this stands for disorder averaging, meaning that I had million of realizations on my computer. I sampled through all of them, added them up, and I divided. That's the simple way. And the conductivity, the average R conductivity, will be given by integral over dr prime, del R alpha, del R beta, alpha beta. And I already specified that I want the DC R conductivity. So omega will be put to 0. Okay. So this is linear up response with respect to the electric field, but it is still exact with respect to disorder. Yes.
This is coming from the Kubo formula?
Yes, yes. This is Kubo formula for a simple case of potential scattering, where we know the Green's function for a given realization of disorder. They are spatial derivatives. So this is component alpha, let's say ddx, and this is ddx prime, or this is ddx and this is dy prime.
Maybe it's useful to go in just a couple of lines.
Okay. First, you say that you apply the vector R potential, which is spatially uniform, but in principle time dependent. You switch to frequency dependence, and then you do a perturbation theory in this vector R potential. Once you have your wave function, you can construct the current, and you can compactly express the bilinears which show up in the R quantum mechanical formula for the current via the Green's function. If you do so, yes. So current, which is measured at point R, is going to be del of R. I'm assuming now simple parabolic spectrum. So I have E of M. This is going to be del of R prime. Then A. No, sorry. You don't have my note? Sure. I thought you printed them out. I thought you printed them out. Okay.
Not a very good.
Okay. So here I have A del R acting on G R R prime. Here I have del R R prime, del R G R prime R, plus the dimagnetic term, which is just proportional to the vector R potential. Okay, so this is, you can think about one wave function. So this is the quantum mechanical expression in terms of the current Y wave functions, where we compress the bilinears into the Green's functions. And this is exact with respect to disorder. So I didn't say what this Green's function is. Then, because I already have a linear relation between the current and the vector R potential, and the electric field is minus dA dt, basically that gives me the R conductivity. And for the DC case, I only need the first term. I don't need the dimagnetic term. Okay, that's how you end up with this R convolution of the Green's functions. Okay? I have more lines in other nodes, but if this looks more or less are convincing. So it's kind of simple. You have a particle which is going from point R to point R prime. Let's say this particle is an electron, and then you have a hole which is going in the time reverse direction from R prime to R. And of course, there should be E squared over M squared. Yeah? Well, so let me put brackets around, because the difficult part of this formula is how we're going to average. No, not yet.
But the R prime.
Oh, R. Once you do this, you put R prime equal to R. Yeah.
So the derivative is after you average it, right?
No,
So,
before.
okay, so you take the derivative and then you do the average.
That doesn't matter. That doesn't matter. The order doesn't matter, because your Green's function is a regular function in R space. Right. What's important though is that the product of the averages is not equal to the average of the product. No, because there's an integral over R prime, right? And before averaging, I will calculate the conductivity measured at point R. But after averaging, it doesn't matter. So after averaging, this object is a function of R minus R prime. If you integrate over R prime, R drops out. So there's only one integral. 5 minutes left, okay. All right. So how do we average? In two ways. So first of all, we need to understand what we mean by this Green's function, right? And now we're going to develop a perturbation theory with respect to disorder. So the Green's function, let's denote it. Let me make it kind of thick. So this is in the presence of disorder. First term is just a free Green's function, right? You go from somewhere, you're totally free. Then you meet an impurity at point, let's say R1. And then you go here from point R to R prime, R to R prime, from R to R1 to R prime here. And then you meet two impurities. So time doesn't matter here because it's all elastic scattering, so it's all at the same frequency. And then to infinite order, right? So now when I substitute these expansions into my conductivity bubble, I will have averaging of two types. So let's say I have a term in which I have two consecutive impurities on the same arm, right? And then I can have two impurities on the opposite arms. Okay? Averaging means that at this point, we met an impurity with potential UR1. Here we have an impurity with potential UR1, UR2. And let's say that the statistical properties are such that average U is equal to 0. And we know the correlation function U of R, U of 0, which is some W of R. Okay? This average will be denoted by a dashed line, meaning that if I have two of them, I will connect them by a dashed line. So in this case, the dashed line will connect 2 points on the same side. In this case, it will connect it on the opposite sides. Okay. This is also the conductivity calculated at 0 temperature. So static conductivity in a Fermi gas at 0 temperature is much smaller than at the Fermi energy, then both frequencies are equal to 0. Yeah, so you're certainly right. I should have done it more carefully. You end up with this G omega R prime, G omega R prime R, derivative of the Fermi function at frequency omega with minus sign, integral over omega. If I replace this by a delta function, all these omegas go to 0. Okay? The external frequency of light is already put to 0. So there is frequency of light and there is frequency of fermion. Right? Frequency of light is equal to 0, then you end up with this. But then you also want to take the 0 temperature limit. And then this R frequency also goes to 0 because of the delta function. Okay, yeah, so this is going to be kind of a pathway to next lecture. If we continue adding up dashed lines here, the sum of these dashed lines here will give us the disorder averaged Green's function, which will have the self energy. The self energy will be coming from the single particle scattering time. Right? This part will give us our vortex R corrections, and there will be several types of them. If I go to next order, I can do ladder type, I can do cross type, and I can do cross type of the second one. The Boltzmann equation, as we looked at it, is equivalent to taking into account impurity scattering for disorder averaged Green's function, which means smearing the states with the self energy and taking the ladder approximation for the vortex R correction. Anything beyond this goes beyond the Boltzmann equation. Okay? In order to understand the resistive anomaly, we'll have to go beyond the Boltzmann equation. So diagrams of this type will be important. All right, let me stop here.
We had quite a few questions, but are there any urgent questions?
Are you putting pressure? A lot of.
But we also
can take some questions. I mean,
okay.
because it's coffee break.
Very, very good point. This is simpler. Okay. For pedagogical purposes, it's just the simplest case, because in this case, I only have the pairwise correlators and nothing else. If I really wanted to describe impurity